The model you are using right now does not know anything about your private notes. It does not know about the document you wrote last week, the research you saved 6 months ago, or the notes scattered across a folder on your machine. It knows what it was trained on, and your private stuff was not in that training data. So when you ask it a question about your own work, it either guesses or it tells you it does not know. I ran into this problem myself and decided to fix it properly. I built a retrieval augmented generation system over my own notes, and along the way I learned what the term actually means, where the real difficulty lives, and when the whole thing is more trouble than it is worth. This video is that walkthrough, built from scratch, in plain terms. What retrieval augmented generation actually means. Before I show you how to build one, let me explain what the words mean, because the name sounds more complicated than the idea. Retrieval augmented generation is a way of giving a language model temporary access to a body of knowledge it was never trained on. The model itself does not change. You do not touch its weights. You do not retrain anything. Instead, when you ask a question, you first search your own data for the most relevant pieces. Then you hand those pieces to the model along with the question and say, "Here is some context, now answer this." The model reads the context you gave it and uses that to give you a better answer. That is the whole idea. The retrieval is the search step. The augmented part is the context you added. The generation is the model writing the answer. 3 steps, and the model only handles the last one. Why you would want this over anything else? So why would you do this instead of just training or fine-tuning the model on your notes? The answer is time, money, and flexibility. Fine-tuning a model means running a training job on your data, which costs real compute, takes real time, and produces a new model you then have to serve. If your notes change tomorrow, you do a new training run. If you want to add one document, you do a new training run. And when the model answers a question, you generally cannot ask it which sentence in your notes it is drawing from, because the knowledge is baked in. With retrieval augmented generation, you keep your data as plain documents. When you update a note, you update the index. Cost is tiny, and every answer the model gives you can be traced back to the exact passage it read, because you chose that passage and handed it over yourself. For anything where the data changes, grows, or needs to be auditable, retrieval usually beats fine-tuning by a wide margin. Fine-tuning earns its place for style and behavior changes, not for keeping the model up to date on facts. Step 1. Chunking your notes. Let me walk through the build now, step by step. The first thing you have to do is cut your notes into small pieces called chunks. A language model has a context window, which is a limit on how much text it can read at once. You cannot paste your entire notes collection into every prompt. So you split the documents into passages, maybe 200 to 400 words each, with a little overlap between adjacent chunks so you do not cut a sentence in half and lose the meaning. The chunking step sounds trivial, and it is the one that causes the most subtle problems later. If your chunks are too long, you waste context space on irrelevant material. If they are too short, you lose enough context that the passages stop making sense on their own. I found that keeping a chunk roughly the size of one coherent thought, one argument, or one explanation works better than any fixed word count rule. The right size depends on your documents, and you probably have to experiment. Step 2. Turning chunks into embeddings. Once you have your chunks, you need a way to search them by meaning, not by keyword. That is where embeddings come in. An embedding is what you get when you run a piece of text through a model that converts it into a list of numbers, usually hundreds or thousands of numbers long. That list of numbers is a point in a high-dimensional space, and the key property is that passages with similar meanings end up near each other in that space, and passages about completely different things end up far apart. You run every chunk through an embedding model and store the result. This is the index you will search later. The embedding model itself can be an API call to a hosted service at a small metered cost, Or you can run a smaller open source model locally if you want to keep everything on your machine. I used a hosted embedding API for my nodes build because the index only needs to be rebuilt when the nodes change, so the cost is small and the calls are infrequent. Step 3. Storing your embeddings. Once you have a list of embeddings, one per chunk, you need to store them somewhere you can search quickly. The tool for this is called a vector store or a vector database. It is a data store optimized for one specific query. Given a new vector, find me the vectors that are closest to it. For a small personal notes collection, you do not need a production database. I stored mine in a simple file on disk, a flat list that I reload into memory at query time. This works fine for thousands of chunks. Once you get into the hundreds of thousands of chunks, or need multiple users querying at once, you would reach for a proper vector database. But for personal notes, the flat file approach is fast enough and much simpler to reason about. The point is the storage is just a lookup table. The magic is in what you do at query time. At step 4, querying the index. Here is where it comes together. You have a question. Maybe you ask, what did I write about reducing Docker image size? Instead of searching your notes by keyword, you embed the question using the same embedding model you used for the chunks. Now you have a vector representing the meaning of the question. You run a nearest neighbor search against your stored chunk vectors and pull out the top 5 or 10 chunks whose vectors are closest to the question vector. Those are the passages most likely to contain the answer. The whole operation takes milliseconds once the index is loaded. And what you get back is not a generic web search result. It is passages from your own notes, ranked by semantic similarity to your question. You have not asked the model anything yet. You have just done a very smart search over your own data. At step 5, stuffing context into the prompt. Now you take those retrieved chunks and you put them into the prompt alongside the question. The structure looks roughly like this. Here are some notes that may be relevant. Here is the question. Answer based on what is in the notes. The model reads the context you gave it and writes an answer. Because the context is right there in the prompt. The model is not guessing from training memory. It is reading the passages you just handed it and synthesizing an answer from them. And because you know exactly which passages you retrieved, you can show the user the sources. You can say, this answer came from these 3 passages in these 2 documents. That traceability is something fine-tuning can almost never give you. And for knowledge work, it matters a lot. Why this approach is honest about its limits? I want to be straight with you about what retriever augmented generation is not. It is not magic. It is search plus a reading model. The quality of the answers is bounded by the quality of the search. If you retrieve the wrong passages, the model will give you a confident answer based on the wrong context. It does not know the context is wrong. It just reads what you handed it. And it will sometimes ignore the context you gave it, especially if the question does not closely match any passage, or if the model has strong prior training that conflicts with your notes. You are adding a retrieval layer, and that layer can fail in its own specific ways that are separate from the model's own limitations. The failure modes. Honestly, let me name the failure modes explicitly so you know what to watch for. Bad chunking is the most common root cause. If you chunked too aggressively and split a thought across 2 pieces, neither chunk will retrieve well for questions about that thought, because neither half scores high enough on its own. The second failure mode is retrieval mismatch, where the question is phrased differently enough from the note that the embedding similarity is low, and the right chunk does not make it into the top results. This happens often with technical jargon, abbreviations, or personal shorthand in your notes. The third is a stale index. If you update or add notes and forget to rebuild the embeddings, you are searching an old snapshot of your data, and you will miss newer material. The fourth is model ignoring context, which is subtle. Sometimes you retrieve exactly the right passage, and the model answers as if it never read it, especially if the passage is short or ambiguous. None of these are unsolvable, but you need to know they exist so you can test for them rather than assuming the system is working. How I tested mine. The way I tested my own notes build was simple. I picked 20 questions I knew the answers to from memory, questions where I knew I had written something relevant. I ran each one through the retrieval pipeline and looked at what came back. I checked whether the right chunks were in the top 5 results, and then I checked whether the final answer matched what I actually wrote. When a question failed, I traced it back to the chunking or the embedding step, not the model step. In almost every case, the problem was upstream, not in the generation. This is the pattern with most retrieval failures. The model is usually not the broken part. The search is. When RAG is overkill. Now let me tell you when you should not build one of these. If your data is small enough to fit in a single prompt, just paste it in. If you have 10 pages of notes and you are using a model with a large context window, you do not need a retrieval layer at all. Just send the whole thing. Retrieval adds complexity, adds a build step, adds an index you have to maintain, and introduces the failure modes I just described. All of that overhead is only worth it when your data is too large to paste or when you need to keep the data fresh and growing over time without a fixed ceiling. The sweet spot for retrieval augmented generation is when you have a large or growing collection of documents. You need to stay up to date as the collection changes, and you want to be able to point to exactly which passages the answer came from. Below that threshold, simpler is better. A model with a big context window and the paste operation is genuinely a fine answer for many use cases. Spend more time on chunking than you think you need to. The retrieval step is only as good as the chunks it searches across. Before you add any smarts to the search or the generation, test whether the right chunk even makes it into the top results for your hardest questions. If it does not, no amount of prompt engineering will save the answer. Get the retrieval right first. Everything else is secondary. And do not over-engineer the storage layer up front. A flat file or a simple SQLite table will handle most personal knowledge bases without any fuss. Start there. Measure whether it is a bottleneck and only add infrastructure if you hit a real limit. The complexity you add to a system has to be paid for in maintenance or forever. So add it only when a simpler thing has already proven it cannot keep up. So that is how I built a retrieval augmented generation system over my own notes. From chunking through embedding, through storage, through querying, through stuffing the context into a prompt. It is not a complicated architecture once you see all 5 steps laid out. The hard part is not writing the code. The hard part is getting the chunking right, testing the retrieval honestly, and knowing when the whole thing is more trouble than it is worth. If you're building something similar, or you want to see more concrete walkthroughs of things I have actually built and run, subscribe and follow along. Thanks for watching, and I will see you in the next one.